I'm Pat Dugas. This screencast is about analyzing the graphs of polynomial functions, specifically their zeros and their turning points or extrema, which include local maximums or minimums. Let's look at some terms first. First of all, the location principle is a zero in a function occurs as its function values change from negative to positive or positive to negative, meaning that they cross the x-axis at that point because they have to go through zero between negative numbers and positive numbers or vice versa. Extrema or turning points occur at relative or local maximums or minimum. And by that I mean this is a point where the value of the function for a maximum is greater than the point surrounding it. And for a minimum, this is the point where the function values are less than those surrounding it. Now, there's a more precise definition of these, and when we get into calculus, so let's dive into the details here. So first of all, when we're trying to find zeros, we're looking for places where a function, such as this green graphed function here, is going from negative values to positive values as we move from left to right. Because as it goes from negative to positive, at some point it passes through zero. I'm going to draw a purple function where the same sort of thing occurs. Okay, so here's a polynomial function, and it's going, as we're moving from left to right on the x-axis, the values of f of x are decreasing from positive into negative. And so at that instant, it goes from positive to negative, we have a zero there. That's what the location principle is all about. Now in finding extrema, which are values where the function is greater than all the points surrounding it, or the function value is less than all the points surrounding it, I'll draw an example of that. So here's a function in purple where I have a local maximum point because all the values of the points surrounding it nearby are less than the value of this f of x. Let's say that f of x was equal to 3. Okay, so that means all the points surrounding it, not necessarily in the entire function because it is a local or relative extrema, relative maximum, all the points surrounding it have output values f of x less than 3. In a similar way, a local minimum occurs. Let's say this occurs at 1. F of x equals 1. Well, this is a local minimum at this value, at this point, because all the points surrounding it have higher f of x values. Now again, that doesn't mean that happens on the entire function. These are called relative minimums and relative maximum because they're only talking about a small local area. If we're looking at the entire function, that's called an absolute minimum or absolute maximum. We're not talking about that today. An important point is that a polynomial of degree n can have no more than n minus 1 turning points or extrema. For example, what I've drawn looks like a third degree function. A third degree function can only have, since its degree is 3, it can only have 2 or less turning points. It could have less, but at the most it has 2. And in this case, this function in fact does have 2 turning points. Let's look at a function in terms of locating the zeros, and then we'll look at it as far as finding the extrema. So we have a function x to the fourth minus x to the third minus 4x squared plus 1. First thing you're going to do in sketching and analyzing function is to make a table of values. Okay, so we do know that this is a fourth degree polynomial because its leading term has a degree 4. And so it is going to have 0, 2, or 4 real roots. That's from the previous screencast. So let's make a table of some values right around 0 from negative 2 all the way up to 3. So we're going to use the idea of the location principle that as the value of f of x changes from positive to negative or negative to positive, we have a 0. Well, we know there's a 0 in between these two values because it goes from positive to negative. We know there's a 0 in between these two values because it goes from negative to positive. And then we know there's a 0 between these two values because it goes from positive to negative. And finally, we know there's another 0 between these two numbers. So this is a very busy function, this fourth degree function. It's got 4 zeros. So it's the case where we have 4 real zeros. Anywhere there's a change in signs from positive to negative or negative to positive means that there has to be a 0 there. And by what we're calling the location principle. So we know there's a 0 between -2 and -1. We know there's a 0 between x equals -1 and 0. We know there's a 0 between 0, x equals 0, and x equals 1. And we know there's a 0 between x equals 2 and x equals 3. Let's look at turning points on the same function. So we're going to try to estimate the x-coordinates where the extreme values of maxima, relative maxima, and relative minimum occur. So again, we use our same table. We're not looking at the end points because that's kind of our end behavior, okay? End behavior, we know this is a 4th degree function and it has a positive coefficient. So we know its end behavior is it's going to increase towards positive infinity at the end. So if we go to the left of -2 and to the right of 3 in the x directions, we know we're going to get even larger positive values. What we're looking for now, though, is points where the value of the function is greater than or less than those of the surrounding points. Well, I see at -1, it appears to be quite a bit smaller than the 9 or the 1. I also see the 1 is greater than the points around it, and the -7 is much less than the points around it. So that doesn't mean the extreme values occur at those points, but they're going to occur very close to it. So since it's a degree 4 function, it has 3 or less turning points. We know now that it has 3, and the extrema occur at those points where a relative minimum or maximum occurred compared to nearby points. So as I said before, at x equals -1, f of x equals -1, much smaller, that's going to be a min, a relative minimum. This 1 is going to be a relative maximum because it's the largest of the points around it. And the -7 is going to be a relative minimum as well. Again, they are relative minimums and maximum. It's not for the entire function behavior. Now, the graph of the function bears this out. And this is our table, and over here, this is our Desmos graph of the function. We said we knew that its end behavior was going off into positive infinity. We knew that it had 4 zeros, and they are on the intervals we thought they were, between -2 and -1, between -1 and 0, between 0 and 1, and between 2 and 3. Finally, we knew that there were 3 extrema. We knew they occurred around x equals -1, around x equals 0, and way down here around x equals 3. Notice you can see it's pretty darn close to x equals -1 and x equals 0 that these relative minima and maximum occur. But this minimum right here doesn't quite occur at x equals 3. It occurs at just a little bit before that. And again, these are relative minimums and maximums. Let's look at it with another example. F of x equals -x to the 5th minus x to the 4th plus 3x to the 3rd minus 2x squared plus 1. We'll make a table. We're going to look at the degree of the function. Well, it's a 5th degree function, and it's odd because 5 is an odd number, and it has a negative leading term. That tells us the end behavior is such that f of x is going to go from positive infinity off to negative infinity in the end, because it's flipped around from the normal negative to positive. And because it's an odd function, it can have at most 5 real zeros. So it's either going to, and it's got to be an odd number. So it's got to have 5, 3, 1, or no real zeros at all. So we already know a fair amount about this function just by that information, which is mostly from our previous screencast. Let's add the things we learned here. Well, looking at zeros, it's got 3 real zeros because I'm looking at sign changes. From -3 to -2, it changes sign. From -1 to 0, it changes sign. And from 1 to 2, it changes sign. And I know that the extreme values aren't, the endpoint values with this end behaviors occurring, I'm not worried about that. I'm worried about the sign changes in between these numbers. And so some point between x equals -3 and x equals -2, we have a 0. Some point between -1 and 0, we have a 0. And also exactly x equals 1. Finally, we know it has 2 turning points, and it's a degree 5 function. So it could actually have as many as 4, but in this case, it only has 2. It has one that occurs somewhere around x equals -2. Why? Because -15 is quite a bit smaller than the numbers around it. It also has a turning point at about 0, 1 because 1 is much bigger than the numbers surrounding it. If we go beyond 2, we're going to get numbers that go down further into negative infinity. If we go to the left of -3, we're going to get numbers that are bigger than 64. So that's our end behavior. And the graph of the function bears this out. So this screencast has been about analyzing the graphs of polynomial functions by taking things we already know and then putting it together with being able to estimate the zeros and extreme values or turning points of the functions.